Hello friends, previously we discussed about the basic structure of the bipolar junction transistor, talked about basic BJT operation, its parameters and characteristics. In today's lecture, we shall be talking about BJT as an amplifier. Amplification is the process of linearly increasing the amplitude of an electrical signal and is one of the major properties of a transistor. We learned that a BJT exhibits current gain called beta, and when a BJT is biased in the active or linear region as previously described, the BE junction has a low resistance due to forward bias and the BC junction has a high resistance due to reverse bias. After completing this section, you should be able to describe how a BJT is used as a voltage amplifier and will be able to identify the DC and AC quantities in an amplifier. Further, we shall be talking about BJT as a switch and as an optocoupler. DC and AC quantities. Before discussing the concept of transistor amplification, the designations that we will use for the circuit quantities of current and voltage must be explained, because amplifier circuits have both DC and AC quantities. In this lecture, italic capital letters are used for both DC and AC currents and voltages. This rule applies to RMS, average, peak and peak to peak AC values. AC current and voltage values are always RMS unless stated otherwise. Although some use lowercase I and V for AC current and voltage, we reserve the use of lowercase I and V only for instantaneous values. In this lecture, the distinction between a DC current or voltage and an AC current or voltage is in the subscript. DC quantities always carry an uppercase Roman non-italic subscript. For example, IB, IC and IE are the DC transistor currents. VBE, VCB and VCE are the DC voltages from one transistor terminal to another. Single subscripted voltages such as VB, VC and VE are DC voltages from the transistor terminal to ground. AC and all time varying quantities always carry a lowercase italic subscript. For example, IB, IC and IE are the AC transistor currents. VBE, VCB and VCE are the AC voltages from one transistor terminal to another. Single subscripted voltages such as VB, VC and VE are AC voltages from the transistor terminal to ground. Voltage amplification. As you have learned, a transistor amplifies current because the collector current is equal to the base current multiplied by the current gain beta. The base current in a transistor is very small compared to the collector and emitter currents. Because of this, the collector current is approximately equal to the emitter current. With this in mind, let us look at this circuit here. An AC voltage Vs is superimposed on the DC bias voltage Vbb by capacitive coupling. The DC bias voltage Vcc is connected to the collector through the collector resistance Rc. The AC input voltage produces an AC base current, which results in a much larger AC collector current. The AC collector current produces an AC voltage across Rc, thus producing an amplified but inverted reproduction of the AC input voltage in the active region of operation. The forward biased base emitter junction presents a very low resistance to the AC signal. This internal AC emitter resistance is designated RE in figure and appears in series with RB. The AC base voltage is VB is equal to IE RE. The AC collector voltage Vc equals the AC voltage drop across R. Vc is equal to IC RC. Since IC is approximately equal to IE, the AC collector voltage Vc is approximately equal to IE RC. Vb can be considered the transistor AC input voltage, where Vb is equal to Vs minus Ib Rb. Vc can be considered the transistor AC output voltage. Since voltage gain is defined as the ratio of the output voltage to the input voltage, the ratio of Vc to Vb is the AC voltage gain AV of the transistor and is given by this equation. Substituting IE RC for Vc and IE RE for Vb yields the equation as shown here. The IE terms cancel, therefore, we get AV as this equation. This proves that the transistor shown in figure provides amplification in the form of voltage gain, which is dependent on the value of RC and RE. Switching operation. Figure here illustrates the basic operation of a BJT as a switching device. In part A, the transistor is in the cutoff region because the base emitter junction is not forward biased. In this condition, there is ideally an open between collector and emitter as indicated by the switch equivalent. In part B, the transistor is in the saturation region because the base emitter junction and the base collector junction are forward biased and the base current is made large enough to cause the collector current to reach its saturation value. In this condition, there is ideally a short between collector and emitter as indicated by the switch equivalent. Actually, a small voltage drop across the transistor of up to a few tenth of volts normally occurs, which is the saturation voltage VCE saturation. Condition in cutoff. As mentioned before, a transistor is in the cutoff region when the base emitter junction is not forward biased. Neglecting leakage current, all of the currents are 0 and VCE is equal to VCC, that is VCE cutoff is equal to VCC. Conditions in saturation. As you have learned, when the base emitter junction is forward biased and there is enough base current to produce a maximum collector current, the transistor is saturated. The formula for collector saturation current is as given here. Since VCE saturation is very small compared to VCC, it can usually be neglected. The minimum value of base current needed to produce saturation is as given by this equation. Normally, IB should be significantly greater than IB minimum to ensure that the transistor is saturated. A simple application of a transistor switch. The transistor in figure is used as a switch to turn the LED on and off. For example, a square wave input voltage with a period of 2 seconds is applied to the input as indicated. When the square wave is at 0 volts, the transistor is in cutoff, and since there is no collector current, the LED does not emit light. When the square wave goes to its high level, the transistor saturates. This forward biases the LED, and the resulting collector current through the LED causes it to emit light. Thus, the LED is on for 1 second and off for 1 second. The phototransistor. In a phototransistor, the base current is produced when light strikes the photosensitive semiconductor base region. The collector base p-n junction is exposed to incident light through a lens opening in the transistor package. When there is no incident light, there is only a small thermally generated collector to emitter leakage current ICEO. This dark current is typically in nanoampere range. When the light strikes the collector base p-n junction, a base current I lambda is produced that is directly proportional to the light intensity. This action produces a collector current that increases with I lambda. Except for the way base current is generated, the phototransistor behaves as a conventional BJT. In many cases, there is no electrical connection to the base. The relationship between the collector current and the light generated base current in a phototransistor is as given by this equation. The schematic symbol and some typical phototransistors are shown here in this figure. Since the actual photo generation of base current occurs in the collector base region, the larger the physical area of this region, the more base current is generated. Thus, a typical phototransistor is designed to offer a large area to the incident light, as this simplified structural diagram indicates. A phototransistor can be either a 2-lead or a 3-lead device. In the 3-lead configuration, the base lead is brought out so that the device can be used as a conventional BJT with or without the additional light sensitivity feature. In the 2-lead configuration, the base is not electrically available and the device can be used only with light as the input. In many applications, the phototransistor is used in the 2-lead version. Figure here shows a phototransistor with a biasing circuit and typical collector characteristic curves. Notice that each individual curve on the graph corresponds to a certain value of light intensity and that the collector current increases with light intensity. Phototransistors are not sensitive to all light, but only to light within a certain range of wavelengths. They are most sensitive to particular wavelengths in the red and infrared part of the spectrum, as shown by the peak of the infrared spectral response curve in figure. Applications. Phototransistors are used in a variety of applications. A light operated relay circuit is shown in the figure here. The phototransistor Q1 drives the BJT Q2. When there is sufficient incident light on Q1, transistor Q2 is driven into saturation and collector current through the relay coil energizes the relay. The diode across the relay coil prevents by its limiting action a large voltage transient from occurring at the collector of Q2 when the transistor turns off. Figure B shows a circuit in which a relay is deactivated by incident light on the phototransistor. When there is insufficient light, transistor Q2 is biased on, keeping the relay energized. When there is sufficient light, phototransistor Q1 turns on. This pulls the base of Q2 low, thus turning Q2 off and de-energizing the relay. Optocouplers. An optocoupler uses an LED optically coupled to a photodiode or a phototransistor in a single package. Two basic types are LED to photodiode and LED to phototransistor as shown in figure here. A key parameter in optocouplers is the CTR, that is current transfer ratio. The CTR is an indication of how efficiently a signal is coupled from input to output and is expressed as the ratio of a change in the LED current to the corresponding change in the photodiode or phototransistor current. It is usually expressed as a percentage. Figure here shows a typical graph of CTR versus forward LED current. For this case, it varies from about 50% to about 110%. Optocouplers are used to isolate sections of a circuit that are incompatible in terms of the voltage levels or currents required. For example, they are used to protect hospital patients from shock when they are connected to monitoring instruments or other devices. They are also used to isolate low current control or signal circuits from noisy power supply circuits or higher current motor and machine circuits. Transistor categories and packaging. BJTs are available in a wide range of package types for various applications. Those with mounting studs or heat sinks are usually power transistors. Low power and medium power transistors are usually found in smaller metal or plastic cases. Still another package classification is for high frequency devices. You should be familiar with common transistor packages and be able to identify the emitter, base and collector terminals. After completing this section, you should be able to identify various types of transistor packages, list 3 broadband transistor categories and identify pin configurations. Manufacturers generally classify bipolar junction transistors into 3 broad categories: general purpose or small signal devices, power devices and RF or radio frequency devices. Although each of these categories to a large degree has its own unique package types, you will find certain types of packages used in more than one device category. Let us look at transistor packages for each of the 3 categories, so that you will be able to recognize a transistor when you see one on a circuit board and have a good idea of what general category it is in. General purpose or small signal transistors. These kind of transistors are generally used for low or medium power amplifiers or switching circuits. The packages are either plastic or metal cases. Certain types of packages contain multiple transistors. Figure here illustrates 2 common plastic cases and a metal can package. This figure shows multiple transistor packages. Some of the multiple transistor packages, such as the dual in line and the small outline, are the same as those used for many integrated circuits. Typical pin configurations are shown so you can identify the emitter, base and collector configurations. The metal tab or the metal case is common to the collector and is thermally connected to a heat sink for heat dissipation. RF transistors. RF transistors are designed to operate at extremely high frequencies and are commonly used for various purposes in communication systems and other high frequency applications. Their unusual shapes and lead configurations are designed to optimize certain high frequency parameters. Figure here shows some examples. This brings us to the end of our discussion on BJT as an amplifier and then as a switch. Thus, we conclude that to operate BJT as an amplifier, the base emitter junction must be forward biased and the base collector junction must be reverse biased. This is called forward reverse bias. The three currents in the transistor are the base current, emitter current and collector current. When a transistor is forward reverse biased, the voltage gain depends on the internal emitter resistance and the external collector resistance. Voltage gain is the ratio of output voltage to input voltage. A transistor can be operated as an electronic switch in cutoff and in saturation. In a phototransistor, base current is produced by incident light. A phototransistor can be either a 2-lead or a 3-lead device. An optocoupler consists of an LED and a photodiode or phototransistor. Optocouplers are used to electrically isolate circuits. So, that is all about bipolar junction transistor as amplifiers, switch and as optocouplers. See you in the next lecture with more on analog circuits. Thank you very much.